Today we're going to look at systems of equations in three variables. So the first we have to compare what we had in the system of equations in two variables to what we're going to do today. So if we look at our two variable system, we've got x and y, two coordinate points, and those are going to be our solutions usually when we're given two equations of a line. So we have an unknown x and an unknown y, and a, b, c, d, e, f are just numbers or constants, or integers, just whatever the problem gives you. So if we were to draw these two lines, our answer or our solution would be this intersection point. Okay. Now, when we look at three equations with three letters or three variables, we're adding another dimension on there. So our Cartesian coordinate plane isn't just x and y. We've got to also include this z-axis, which would kind of be poking out of your screen right now if we could do that in 3D. And this would be going backward into the screen. So a plane, two planes intersect, or I guess since there's three equations, we've got three planes that are intersecting, and they might look like this. Here's one plane, and here's another plane intersecting with that one, and then here's a third plane. Intersecting there. So you can kind of see that depending on how your planes are intersecting, we're going to get three coordinates x, y, and z when they intersect at exactly one point. So this happens, three variables happens in three-dimensional space. So if we look at two dimensions, we can either have one solution when they intersect at one point, zero solutions when the two lines are parallel, and an infinite amount of solutions when the two lines lie on top of one another. Now, with three-dimensional space, we can either have one solution where, again, the planes all intersect at one point. We can have an infinite amount of solutions, and this is just one example of an infinite amount of solutions with the line, or with their intersection being a line. And then we can have zero solutions where the planes don't intersect at all, or maybe two of them intersect but not all three of them intersect each other. So what are the steps to solving a system of three equations? So we are going to use one pair of the original equations to eliminate a variable. So get rid of one of the letters. Then we're going to use a different pair of equations to eliminate that same variable. This is important. You want to eliminate the same letter each time you're doing this. The reason is we want to come up with two equations that have the same two letters in them. That way, for step 3, we can solve the system of two equations using methods that we already know how to use, whether that's elimination, substitution, or to solve for y and solve by graphing. We know how to do those. And then lastly, once we have our two solutions from this little sub-problem that we created, we want to plug in the two solved variables into one of the original equations to find the last variable. So let's go ahead and practice that by doing an example. So we want to solve this system. So let's go ahead and choose a variable to get rid of. It looks like y might be easy to get rid of. So let's use the first two equations, and I'm going to multiply the bottom one by 2. So the first equation will stay the same, and the second equation will become negative 8x plus 2y minus 10z is equal to negative 72. Okay, and when we add those equations together, we will get negative 5x, y's cancel, minus 6z is equal to, let's see, that is going to be negative 7 negative 37. Okay, now this is going to be one of my equations that I'm going to use for the little sub-problem within this problem. So now I'm going to choose another two equations from here. I'm going to choose these two because, again, y looks, well, we have to eliminate y again, but it looks like it could be simple to eliminate that. I'm going to multiply this one by 3, so that'll be negative 12x plus 3y minus 15z is equal to negative, let's see, 108. And then the second equation will stay the same. And we add the two equations together, and we will get negative 7x, y's cancel, minus 12z is equal to, let's see, negative 77. And that's my other equation that I'm going to use for my sub-problem. So let's go ahead and write those two next to each other. So negative 5x minus 6z equals negative 37. Negative 7x minus 12z equals negative 77. Okay, now we want to eliminate, or I guess I want to use elimination. You can use substitution or graphing if you want to. I'm going to eliminate the z's, and I'm going to multiply this one by negative 2. So this equation will remain, the second one will remain the same, and then our top one will become 10x plus 12z is equal to positive 74. And again, our second one remains the same. So when we add those together, we get 3x, z's cancel, equals negative 3. So x is going to equal negative 1. Now we can plug that back in to one of our equations up here to solve for z. So that's going to be negative 5, I'm going to choose the top one, times negative 1, minus 6z, and that's going to be equal to negative 37. Well, negative 5 times negative 1 is 5, so if we subtract the 5 over, we'll get negative 6z is equal to negative 42. So z will equal 7. And now our last step is to plug that back into one of our original equations to try to figure out what y is. So when we do that, I'm going to choose the top equation. So that's going to be 3 times negative 1 minus 2y plus 4 times 7 equals 35. So that's negative 3 minus 2y plus 28 equals 35. And then that's 25 minus 2y equals 35. So negative 2y is going to equal 10. So y is equal to negative 5. So then our solution will be the coordinate points negative 1, negative 5, and 7. And let's go ahead and let's bold that box.